Here's the fun part. Okay, look down here. This is a piece of scheme code. It's the procedure append. It takes two lists. It says if the first list is empty, return the second list. Otherwise, cons the first element of the first list onto append coulter of the first list to the second list. Right? You've seen this before back in chapter 2. And it should all be totally familiar to you. So now look up here where it says AA, pretend it says add assertion. This is a, because the query system doesn't have a load command, but scheme does. So AA is a scheme procedure that is equivalent to the assert bang thing in query system. So here are the rules. There's two rules, this one and this one. And as we talk about them, I'd like you to compare them to the scheme code. So the scheme code has two cases, the base case and the recursive case. And the two rules correspond to those two cases. So the one that's highlighted now corresponds to the base case. In the scheme code, the base case says, if A is empty, return B. This rule says the relation append holds for the empty list, any list Y, and that same list Y. In other words, if you append the empty list to anything, you get the anything. Okay? Everybody clear on the relation, on the connection between this append rule and the base case of the append program? Okay, a couple of sidewayses. Somebody ask a question. So we're comparing this rule with just this much of the scheme code. If the first argument is empty, return the second argument. This says if the first list is empty, and here's the second list. This is like B. It's like this is the A value, this empty list, and this variable Y is the B value in the original scheme code. So empty list appended to B gives B, and the same thing here. Yeah? Okay, I'm going to move on. Now let's look at the other rule. That's a little more complicated. First, we'll look at the scheme code. What if A isn't empty? This says split it up into its first element and the rest of it, its car and its coulter. And we're going to recursively compute append coulter A, B, and we're going to stick car of A in front of that. Okay? And that's going to be the result. So the result of append where the first argument is not empty is a pair, because cons makes a pair. The car of this output pair is the car of the first argument. The coulter of the output pair is the result of doing this append. Okay? So now let's look at the conclusion of this rule. So first of all, this rule applies only in the case where A is a non-empty list. Right? That's like the if in the scheme code. Only if null A is false do we get to that cons. So since the first argument is non-empty, we can think about it in terms of its car and its coulter. That's what this is. This is scheme dotted pair notation. It says this argument is a pair whose car we're going to call U and whose coulter we're going to call V. Okay, so question mark U is car A. Question mark V is cooter A. And then question mark Y is B. Right? Okay, well, we don't have to divide B, I'm going to have to divide Y here into its car and its cooter because the scheme code doesn't divide B into its car and its cooter. The only use of B is right down here, right? It's the whole B. So A is replaced by this pair U dot V. B is replaced by the variable Y. And now what do we know about the result in this case? It should be a pair, because of that cons, whose car is equal to the car of A. Now, what you're going to be tempted to do, every single one of you, is going to be tempted to say something like question mark U dot append question mark V question mark Y. Right? Because you're going to want to take the cooter of A and append it to B. If I had some red chalk, I'd use it, but I don't, so I'll just do that. There's no composition of functions in query system because there's no functions, first of all, in the query system. So what can we do? Well, I don't have an exact expression that I can put in here yet. So I'm just going to make a variable, z, which is the cooter of the result. And then I'm going to assert something about the relationships among these variables that gives me the right value of z. Namely, z should be the result of appending v with y. That's what this says. So if we get a query, an append query, in which the first thing is a non-empty list and the last thing is a non-empty list, and if the cooters match up, there's this question mark u here and question mark u here. If the same variable occurs twice, it has to match the same thing. And then we evaluate the body of the rule, which is this recursive invocation of the same rule. It says, I want to assert, or in order for this thing to be true, in order for this rule to match the original query, it has to be the case that appending cooter of A to B gives cooter of the result. Okay? And it's a little bit of a convoluted way to think if you're not accustomed to it. But it gives us some remarkable results. I can say append A, B, C, D, E, A, B, C, D, E. Oops, what happened? Did it not load? Wait, I'm really confused. Nope. All right, let's try this again. Oh, I'm still in SDK. Whoops. I'm in variable GDL, but I defined it. Okay, let's try again. Hope this works, because it's kind of the big moment of the lecture coming up. Yes, query results. There we go. So that's not a big surprise. But I can say append ABC to what gives ABCDE. That works. I can say append what to DE gives ABCDE. And that works. And finally, I can say append XY to get ABCDE. What are all the things I can append to each other to get ABCDE? And here they are. Okay? Functions won't do that. Only relations will do this piece of magic.